the context of supervised learning, we saw that regression is an important class of problems where you try to look at coming up with a curve explaining the output in terms of several input functions and try to interpolate the function as the model representing the classical historical data. In terms of how you would like to approach the correctness of a regression model, it is based on the idea that you need to basically have some notion of error. The model or the equation you are deriving for describing the output in terms of the input functions, you should have some notion of the output for the corresponding function by means of the error of the output function. So we look at some of the popular error metrics when we look at measuring the effectiveness or what do you say, correctness of a regression model. If you take a regression model and plot a function along with the original raw data, you will always typically find that there is absolutely no way all the points fall exactly on the function you have approximated. The reason is you typically tend to create a generalizable function or an equation which has predictive performance, and you do not want to compromise your future predictability by overfitting the function for your current input data. So there is bound to be some notion of error which is effectively a gap between the predicted data and your actual data. So what we can say is this is some notion of fitted data, which is your predicted or equation model data, minus actual data. So for the same input data, you get 2 points. One is actual data, and you also get something which is predicted or fitted based on your function which you have computed or the research you have computed. So this error gives you a reflection of how correct your regression model is. So in terms of regression evaluation measures, in a supervised learning, you typically look at any notion that gives you an idea of the error. So the most common error function which is used is known as mean absolute error. Mean absolute error is basically if you have I equal to 1 to say n different observations, absolutely. So what this is, it says that if for a specific ith row, yi is the actual value and your predicted value is yi, then the absolute distance between the two, absolute gap between the two, you sum the absolute gap over all the input samples, then that gives you the mean absolute error. So mean absolute error is basically a way of computing the total error as depicted by your fitted function or the regressor. While mean absolute error is a good function, but a better approximator for the same is actually sigma y minus by n, because we need to look at what is the total number of observations and divided by it. So that becomes the mean absolute error. Total absolute error divided by total number of observations. A correspondingly similar but more popular approach to defining the error function is what is known as RMSE, which is nothing but, it is basically square root of sigma of yi minus y pred I whole square. So the sum of the squares of the gap between y pred I and yi, you sum it over, that becomes what is called a sum of squared errors, and then you take the square root of that and divide it by n. That becomes mean squared error. So what the advantage of mean squared error is, it is independent of the direction in which you are actually computing, and it's supposedly a more moderate prescription of the error as compared to mean absolute error. So what RMSE does is it gives a way of identifying how good or accurate a regressive function is by looking at how much of the predicted function is deviating from the original values by squaring the differences, summing it over, getting the sum of square, doing the square root and dividing by n. So that becomes root mean square error, which is a very popular technique in evaluating how effective a regression measure is. On the other hand, if you want to compute this for different data sets in a normative manner, the issue with RMSE or absolute error is dependent upon how the range of the corresponding observation looks like. For example, if something is measured in kilometers, this gives something in kilometers squared. Something is measured in meters, it gives a measures in thousands. So the unit of measure makes a lot of difference in terms of the absolute quantity of the error depicted by RMSE or the absolute error. There is no normative measure there. So to arrive at the normative measure, what people have done is they have come up with a notion of a normative measure which is unitless. Means it does not depend on whether you are measuring kilometers, meters, kilograms, grams or whatever, but it is normative. So what they do is they compute something known as R square. R square is basically sum of squared errors divided by sum of the distance from the mean. So what it does is it looks at the sum of the squared errors like in RMSE or in mean square error, but it divides by the spread from the mean. So this gives you an idea of a normative approach which is unitless, because you're dividing SSE in one unit divided by same measure squared of distance from the mean. So what happens is this is a normative measure. If R square is 1 or close to 1 means very good regressor. If R square is close to 0, that means it is as good as the mean. If it is minus 1 or below, that means that it is a bad measure. So that way we are talking about a specific application of an evaluation measure which is normative, unitless, and is a better indicator of how effective a regressor is in compared to any unit of measure for the corresponding input variable.